Hey, what's up? Mr. Sutta here. Today we're going to be talking about our introduction to chemistry. We're going to be talking about matter, that's the stuff all around us, and we're going to be talking about the things that make up matter, namely elements, compounds, and mixtures, and what those things are made up of. All right, let's get started. All right, so matter. Matter is anything that has mass or has mass and take up space is matter. So if it has a volume and has a mass, it is matter, right? Matter is made up of tiny pieces, and those tiny pieces are called atoms. Atoms can be considered the building blocks of matter. Everything is made of atoms, everything you touch on a daily basis, right? The types of atoms and matter and how they attach each other give matter its properties, right? So based upon what types of atoms they are and then how they're attached to each other, that's what makes, let's say, for example, a piece of plastic different from a piece of metal. All right, so elements are substances that are only made of one type of atoms. Elements cannot be broken down into any simpler substances. Examples of elements are sulfur, which is commonly used as fertilizer. You might find it as hard water in your local water systems. Silver is a common element. Used to be used in silverware back when we had kings and queens. It's also used as jewelry. Copper, commonly used for electrical wiring in your house. Gold, again, commonly used for jewelry. And zinc and copper are also two examples of elements. When they're combined, they make brass, which is commonly used to make instruments. Brass is an example not of an element, but of a homogeneous mixture, right? But all these other ones here, silver, copper, gold, zinc, all of these are elements. They can't be broken down into anything further. They're as small as they can be, right? And here's gold on the side. All right, so let's talk about the structure of our atoms. So we have three different subatomic particles that make up an atom. We have protons. Protons are particles that have a positive electric charge. Neutrons have no electric charge, and these protons and neutrons are found inside the nucleus of an atom. Our last subatomic particle are electrons. Electrons are particles with a negative electric charge. So P, protons positive. We have neutral neutrons with no electric charge. Both of the protons and neutrons are found inside the nucleus, and our electrons, they have a negative charge. Right? And the electrons don't exist in the nucleus. The electrons are found outside the nucleus in what's called the electron cloud. So the protons and the neutrons are packed closer together, and the electrons kind of like buzz around them like little flies in an electron cloud. Right? So here's two examples of what an atom might look up close or zoomed really far in. It's very difficult to tell because a lot of our understandings of atoms are theoretical, which means we can't like see them like you would see like maybe blood or like a bacteria underneath a microscope. But instead we have these diagrams which help us to imagine what the atom might look like. So here's my nucleus with my protons and neutrons in the center, and then my electrons buzz all around them, my electron cloud. Same thing in this picture on the right. Here's my nucleus and my protons all packed together inside my nucleus here, and my electrons and this electron cloud moving around outside the nucleus. All right, so properties of our subatomic particles. Again, we got three of them. Our protons are positive, and they're located in the nucleus. Our neutrons are neutral. They have no charge, and they're, again, located in the nucleus. And our electrons are negative, and they are located in the electron cloud. All right, our atomic number, that's the number of protons in an atom. Our atomic number is equal to those number of protons for that specific element. This is the whole number in the elements box on the periodic table of elements. In a neutral atom, the number of protons is equal to the number of electrons. And that formula is atomic number is equal to the number of protons, which is equal to the number of electrons. All right, so here's my periodic table of elements. All these little tiny numbers on the top, those are our atomic numbers. So example, if we're looking at 5 up here, that's boron. Boron's atomic number is 5. Boron always has 5 protons. For example, phosphorus here, atomic number 15. Phosphorus always has 15 protons, and if it's neutral, it also has 15 electrons. All right, so what about neutrons? How do we find those? The mass number of an atom is equal to the number of protons plus the number of neutrons. The mass number is this number on the bottom. So the number on the top is our atomic number, the number on the bottom is our mass number. All right. Our mass number is equal to the number of protons plus the number of neutrons. So here's our formula. Number of neutrons is equal to the mass number minus the atomic number. Right, so this is a helium atom. It has a mass number of 4, the protons plus the neutrons. So it has an atomic number 2. Right, isotopes. Atoms of the same element that have different numbers of neutrons are called isotopes. We're not going to talk about too much about isotopes this year, but they do have some cool and unique uses. For example, some radioactive isotopes are used by doctors to treat certain types of cancer, and geologists use isotopes to determine the ages of some rocks and fossils. This is how we can determine the relative age of the Earth. For example, they found zircon crystals in Australia, and geologists were able to use radioactive isotopes in those crystals to find out that our Earth was over 3 billion years old. And we call that process radioactive dating. Right, so this is how our isotopes work. So usually carbon, atomic number 6, usually has 12 is usually its mass number. It usually has 6 neutrons. Sometimes, though, the mass number can be a little bit higher, 14, in which case we have 8 neutrons. So usually has 6 neutrons, sometimes has 8 neutrons. The atom of carbon doesn't like to have the 8 neutrons. It doesn't like to have the extra neutrons. It wants to be carbon 12 here. It doesn't want to be carbon 14. So this carbon 14 will decay. It means it'll break down over time into that carbon. It'll go from carbon 14 and break down into carbon 12. And by comparing the amounts of carbon 14 to the amounts of carbon 12 that are broken down, we can estimate the time that something has been breaking down for and then get its relative date. All right, so different combinations of atoms. When atoms of more than one element combine, they form what's known as a compound. So a compound contains atoms of more than one type of element that are chemically bonded together. You can see chemically here starts with a C, compound starts with a C. These are chemical compounds. Compounds are chemically combined. Right, so for example, water is a compound consisting of two molecules, made up of one oxygen atom bonded to two hydrogen atoms. So oxygen by itself is an element, hydrogen by itself is an element, but when we combine oxygen and hydrogen, we get water, which is a compound, and the oxygen and the hydrogen are chemically combined. All right, the forces that hold atoms and compounds in place, they are called chemical bonds. So our chemical bonds hold our elements together and form them into a compound. Right, here's an example of water. So here's the oxygen, here are the two hydrogens, and these little black lines represent chemical bonds holding the water molecule together. All right, so if it's not a compound, maybe it's a mixture. Right, so a mixture is composed of two or more substances that are not chemically combined. So very important here, in a mixture, things are not chemically combined. There are two types of mixtures. There are heterogeneous mixtures, where the components are not mixed evenly and each retains its own properties. So for example, trail mix is a heterogeneous mixture. All the components are not really mixed evenly and each retains its own properties. So the raisins and the M&Ms aren't combining to make one weird raisin M&M. The raisins and the M&Ms are together, but they're still their own separate pieces. The other type of mixture is a homogeneous mixture, where everything is the same. The prefix homo means the same. The prefix hetero means different. So in a heterogeneous mixture, all the things look different. In a homogeneous mixture, homo means the same. All the things look the same. So in a homogeneous mixture, you can't see the individual components. They're mixed evenly throughout. So it's also known as a solution. An example is soda, air, or cake. So when we're looking at it, you can't tell the difference between all the stuff that makes up the soda, all the elements that make up the air, and all of the pieces that make up the cake. It all kind of looks the same throughout. Right? So here's my heterogeneous mixture. with my trail mix, you can see the M&Ms and the almonds and the peanuts are all mixed together, but they're still retaining their own properties, right? The M&Ms are still M&Ms, the almonds are still almonds, the raisins are still raisins. To contrast, when we have a homogeneous mixture, you can't see the individual components. They're mixed evenly throughout. So on the right, we have some, what looks like maybe like a flat soda right there. You can't tell apart all the different things which make up the soda there. They're mixed evenly throughout, so it's too tough to tell. Or if we look at this batter on the left, when you mix your batter really well, it all looks the same throughout. So it's a homogeneous mixture. They're physically combined, but they're not chemically combined, right? But a homogeneous mixture, they look the same. A heterogeneous mixture, they look different. And remember, a mixture is composed of two or more substances, but they're not chemically combined. All right, that wraps it up for our introduction into chemistry. Thanks for watching. I hope you learned something, and I'll see you in the next video.